Welcome back to the CMCC Mechanochemistry Discussions. This seminar series is hosted by the NSF Center for Mechanical Control of Chemistry. The goal of this seminar series is to bring the community together. Each seminar is about 30 minutes with 10 minutes of Q&A. The seminar is hosted and streamed live on YouTube on the third Thursday of every month at 10 a.m. Central, but also made available later to watch anytime on YouTube. We have an excellent lineup of speakers for 2021, the first four of whom are shown here. We're very excited about the next series of speakers. Note on Q&A, the webinar is being recorded. However, during the seminar, if you have questions, you may email them to cmccdiscussions@gmail.com and we'll migrate your question to the speaker. Or if you have an account, you can post your questions directly in YouTube. However, note that we reserve the right to remove comments from YouTube that don't adhere to CMCC's values of inclusion and respect. Before we get started, a great big thanks to three people: Dr. James Batiste, the director of the CMCC, Noah Sheehan, a student who's coordinating the webinar for us, and Jennifer Belsick, the administrative coordinator for the CMCC. Thank you so much for joining us. Please do follow us on YouTube and watch all of our mechanochemistry discussions, and stay tuned also on Twitter to keep apprised of our latest updates. Without further ado, today's speaker is Dr. Eva Zurek. Dr. Zurek studied chemistry and physics at the University of Calgary, Canada. She was awarded a PhD fellowship from the Max Planck Research School for Advanced Materials and obtained her doctorate at the University of Stuttgart. After a postdoctoral fellowship at Cornell, she joined the Department of Chemistry at the University of Buffalo SUNY in 2009. Dr. Zurek's research interests include the electronic structure, properties, and reactivity of superhard, superconducting, quantum, and planetary materials, materials at extreme conditions, catalysts, as well as solvated electrons and electrides. She develops the XtalOpt evolutionary algorithm for crystal structure prediction and applies it in materials discovery. Her honors include the Alfred P. Sloan Fellowship and Quantum Systems in Chemistry and Physics Promising Young Scientist Award. She was also elected member at large for APS's DCOMP. Without further ado, we are very honored to have Dr. Eva Zurek here today to talk to us about theoretical predictions of superconducting and superhard materials.
Okay, so thank you very much for the invitation to give a talk at this exciting new center. I'm going to be talking about how one can theoretically predict superconducting and superhard materials, and in particular those that can be made under conditions of pressure. So under pressure, a lot of new exciting chemistry can happen. We are used to pressures of 1 atmosphere because we live on the Earth's surface. But if you go into the center of the Earth, the pressure reaches up to 3.5 million atmospheres. And the unit of pressure that I will be giving in this talk is the gigapascal. So 3.5 million atmospheres is approximately 350 gigapascals. So what happens under pressure? Obviously, the volume contracts. And therefore, it's not just the free energy, but the free energy that includes the pressure volume term that is important in determining which structures are going to be the most stable. And at the types of pressures that I'm going to be talking about here, on the order of 100 to 300 gigapascals, the pressure volume term can actually be much more larger in magnitude than the internal energy of the phases. So where is pressure important? Well, as I've just alluded to, it's important in geosciences and planetary sciences. If you look at the giant planets such as Jupiter and Saturn, the pressure can be on the order of terapascals in the cores. It's important in nuclear weapons research when we have nuclear explosions. The pressures and temperatures are extremely high. And for us chemists, pressure is important in high pressure chemical synthesis, and it can be employed to make, for example, unique materials used for quantum information sciences, and in superhard materials and superconductors, which is what I'm going to be discussing here. And pressure has a large number of different orders of magnitude within the galaxy and the universe. For example, in intergalactic space, it's on the order of 10 to the minus 32 atmospheres, whereas if you go to the center of the neutron star, it's 10 to the plus 32 atmospheres. Therefore, the chemistry that we experience at 1 atmosphere is just only a subset of the chemistry that can happen within the whole universe. And in fact, I'm part of another NSF center, the Physics Frontier Center. That is the Center for Matter at Atomic Pressures, which just started recently. And the mission that we have is to study the nature and implications for massive objects throughout the universe and the potential for revolutionary states of matter that can be formed under high pressure. So some examples here are shown that under pressure, we can have a form of ice, which is superionic, and that is one where the oxygen atoms stay put on their lattice sites. However, the hydrogen atoms can diffuse throughout the system, and it has been shown that this type of form of matter can be black and hot ice. Jupiter, on the other hand, has a core of liquid metallic hydrogen, and it has been proposed that liquid metallic hydrogen, for example, could potentially be superconducting and have other very unique properties. So how does one achieve high pressure? In experiments, one way to do this is by using diamond anvil cells, shown here, and that is able to produce pressures that are static. So pressure is force over area. Therefore, if you have a diamond anvil cell where the tip is very small, you're going to be able to get higher pressures. And using conventional diamond anvil cells, I guess the pressures that one can realize are on the order of 300 gigapascals. However, there have been new technologies made available where you shape the tip of the diamond anvil cell into a toroidal shape. And these types of techniques can reach even higher pressures on the order of 500 gigapascals. Dynamic pressures can be achieved by using shock compression, for example, at the National Fission Facility or in Rochester at the Omega Laser Lab. And here we have these huge sample chambers where lasers are focused to impact on this type of a hologram. And the lasers then interact with the gold can, which produces X-rays. The X-rays are then absorbed by the sample, and because of the sample explodes out and everything else explodes in, and pressures can be generated are extremely high on the order of terapascals in this way, and also the temperatures are very, very hot. So these types of dynamic compression experiments can be done, like I said, at a number of different user facilities. And most of the work that I'll be talking about within the discussion right here will be focused on the types of static pressures that can be achieved. And in computations, using one can change the pressure just by changing the volume of the unit cell. So it's actually just much easier in computations to study these types of systems than it is using experimental techniques. One of the places where high pressure has been shown to have revolutionary advancements is in the area of searching for room temperature superconductivity. So here I show the TC, superconducting critical temperature, versus the time. And as you can see, we have a steady increase in TC with the high temperature oxide revolution in the 90s shown right here. However, after that, the TC did not increase for quite a long time until we see this nice increase in the pink cells. And these revolutions right here occurred because of the high pressure research. It was speculated already a long time ago by Neil Ashcroft that metallic hydrogen could be a high temperature superconductor within BCS theory because of the large electron phonon coupling, no screening by core electrons, and the covalent bonding. Moreover, the BCS superconductors are suggested to have wide bands, which would happen within the hydrogen under pressure. And hydrogen has large vibrational frequencies due to its light mass, and it would have a large density of states at the Fermi level. However, in experiments, it has been really difficult to metallize hydrogen, and so far superconductivity has not been measured in a sample of hydrogen compressed to very high pressures. Therefore, Neil Ashcroft also proposed much later in the night that if we had hydrogen-rich alloys, the chemistry would be able to pre-compress the hydrogen, and it would be much easier at lower pressures to achieve states that would have similar properties as pure metallic hydrogen, that is the large electron phonon coupling, large vibrational frequencies, and so on. And therefore, we could get room temperature superconductivity potentially at lower pressures than within pure hydrogen. So these types of this type of research thinking has brought about a lot of research, computational, and more recently experimental breakthroughs that have yielded really high superconducting critical temperatures, starting first in a sample of compressed hydrogen sulfide, and then going on to the recent discovery of room temperature superconductivity. So here I show some of the experimental results. What is really fascinating here is that the experiments have been closely integrated with theory. In some cases, for example, this discovery of superconductivity at 203 Kelvin, the experiments and the theory came out more or less at the same time. And in other cases, for example, the discovery of superconductivity in this lanthanum H10 phase, the theoretical calculations actually predicted the target material prior to its synthesis. So this is a true example of materials by design. Most recently, there has even been the discovery of room temperature superconductivity in an unknown phase that contained a carbon, sulfur, and hydrogen. And here I show the pressure versus TC plot. So we can see that the highest TC achieved was at about 260 GPa, and it was right almost at room temperature. However, the identity of this phase is still somewhat unknown. So how do we predict these very strange phases? As I've just mentioned to you, you could have SH3 or lanthanum H10 potentially. And this is a problem for experiments, obviously, because experiments cannot be used to probe the positions of the hydrogen atoms. So how do we determine what the structure is, what the crystal structure is, and also how do we as chemists figure out what these potential structures could be, because they are just completely unknown, and using any types of data mining techniques, we would not be able to find them in a database or to use our chemical imagination to come up with these types of structures. So this is where we turn to computational prediction. And there are a number of methods where we can predict crystal structures. In my group, what we do is we use evolutionary algorithms. So the idea of the evolutionary algorithm is that we first produce some sort of random structure or seed a structure with likely prototypes. These structures then go out to our favorite DFT code. They get optimized to the nearest local energy minimum. Afterwards, our algorithm looks to see which structures are the most stable. And then it can take the most stable structures and mutate them in some ways, or take two parent structures and breed them to make a single child structure. Then these go out to be optimized to the nearest local minimum. And then you just repeat this process until hopefully you have converged to find the most stable global minimum for the desired stoichiometry that you're looking at, and then compute its properties. So we've developed an algorithm to do this. It's called XtalOpt. XtalOpt is cross-platform. It can also work with a variety of local queuing systems, codes, including those based on density functional theory and interatomic potentials. And it's available under open source licenses such as GPL and BSD. It comes also with this nice graphical user interface, and it is interfaced with Avogadro, which is a very nice way that one can use to analyze, create, and visualize chemical systems. XtalOpt has been recently developed. Here is a recent feature article where the developments have been summarized, so it can be used to study and predict the unit cells of much larger systems than was previously possible. I will not go into all of our recent developments. Here I just show recent benchmarks that were carried out on a supercell of the strontium titanate. So this has, I believe, 50 atoms in the unit cell. And whereas in previous tests, XtalOpt was unable to, the first version of XtalOpt was unable to reliably find the global minimum structure, we can see that our new techniques are able to find the global minimum structure with up to 100% success rate using, for example, this mitosis or cell splitting type techniques. So here I show also a recent review that we have written, taking a look at the periodic table of superconducting binary hydrides. The types of crystal structure prediction techniques that I have just discussed, as well as many other groups, have theoretically predicted the types of binary hydrides that might be stable under pressure, and then used BCS theory to estimate their electron-photon coupling and their critical superconducting critical temperatures. And what we find for the binary hydrides is that there are two regions within the periodic table that have particularly high TCs. One of them, as I've denoted to earlier, is in this region of the p-block elements and around sulfur, selenium, tellurium. And the other one is around the region of the alkaline earths and rare earth hydrides. And what we find for the binary hydrides that have the highest TC values, such as yttrium lanthanum hydrides, is that the hydrogenic lattices assume these types of very interesting clathrate-like cage structures, and the metal atom is situated within the clathrate. So they have these types of three-dimensional hydrogenic lattices, which is very unusual, taking into account the idea of what we have bonding of hydrogen at 1 atmosphere. There are other hydrogenic motifs that have been observed as well. For example, atomistic hydrogenic lattices or other unique motifs such as one-dimensional or two-dimensional sheets and these types of fused five-membered rings. However, these typically have lower estimated TC values than the clathrate gauges. So one of my collaborators, Ranga Diaz at the University of Rochester, recently made a yttrium hydride phase whose TC he was able to measure. However, because of the problem that these systems have so much hydrogen, Ranga wanted to use a novel characterization technique within Raman spectroscopy to characterize the phases. So he was able to attain the Raman spectrum of the phase as a function of pressure, and wanted to work with us theoreticians to see if we could try to identify what the phase could be. And as I note here, the superconducting critical temperature that Ranga's group measured was the highest one was on the order of 256 Kelvin at 180 gigapascals. So we computed the Raman spectra of these three phases, these three clathrate phases, YH6, YH9, and YH10. And note that the Raman is taken within a diamond anvil cell. So there is a region where we do not see any peaks because they're obscured by those of the diamond. And if we obscure that region from our calculated results, we see that the structure cannot be YH6 because it would not have any Raman visible peaks. There is a YH9 insulating phase that was also predicted by theory. It does also not have any peaks within the region, the frequency region that Rhomba observed. It does, however, have a very high frequency peak. So this cannot be the structure that was synthesized. So YH9 or YH10 are possibilities. However, the peaks are a better match to YH9, which is therefore why we characterize this species to be YH9. Moreover, the volume is in better agreement with experiments, and we believe that the TC is also in good agreement with what was measured and what was theoretically calculated. So here we show what the vibron looks like as a function of pressure. And we note that there is a relatively good match between the experiment and the theory. However, the experimental lines are at a somewhat higher frequency, which is actually in line with our calibration results that were calculated on pure H2 and compared to the experimental measurement of the H2 vibron of pure H2 as a function of pressure. Moreover, the calculated Raman spectra for YD9 is in very good agreement with that obtained experimentally. That proves again that this is likely to be the clathrate phase shown right here. Another system that we have looked at is ternary hydrides, because all of the binary hydrides have been explored to date. As I mentioned previously, the H3S phase has shown to have quite high TC. So it was not it was a good idea to think of mixing hydrogen sulfur with other elements. And in this case, we chose carbon. And theoretical crystal structure prediction searches were carried out on a variety of CSHN structures. And what we found is that this CSH7 phase stood out to be particularly stable. It was not a thermodynamic minimum. It was always a metastable phase, meaning that it lay above the convex hull. This was stable with respect to the elemental phases. However, it was unstable with respect to methane plus H3S, as well as methane, H2S, and 1/2 H2. But it was dynamically stable. And I note that in these types of high pressure experiments, where you laser heat often to promote the formation of the species, it is not quite well known whether or not the species that you are going to be making is kinetically controlled or thermodynamically controlled. So we predicted a number of metastable phases, and all of them were built from this type of building block, where you take one of these interpenetrating H3S lattices and replace it with a methane molecule. And then you can imagine different sized supercells where you have different methane molecules in different cells, neighboring cells, rotated slightly differently. So we predicted a number of phases that were most stable at different pressures, with this PNMA phase most stable at high pressures. The TC and electronic structure of the phases were calculated using density functional theory calculations. And what is the most important point to take away from here is that the electronic structure near the Fermi level arose from the sulfur and the hydrogen atoms. And therefore, the SH framework is what is going to be responsible for the superconductivity. And here I show the estimates of the superconducting critical temperatures that we obtained, with the highest calculated TC value on the order of 190 Kelvin at 150 gigapascals. Now, these values do not match those that were then later measured and published for the carbonaceous sulfur hydride phase that I discussed in the introduction. And therefore, we believe that the phase that was made in experiments differs from the one that we calculated here, and most likely we believe based upon the some recent calculations that have been carried out by us and by other groups, is that the carbon content of the phases considered in our initial study was too high, and we should be looking at phases with lower carbon content. So other ternary hydrides that we have considered are those containing calcium, sulfur, and hydrogen. And here I show what is called a convex hull. If you plot the enthalpies of formation of your species on these types of 3D convex hull, you can figure out which species are going to be thermodynamically stable. Those are the ones that lie on the convex hull, and those that are slightly above the convex hull can be metastable, provided that their phonons are all real. So that means that they are kinetically stable. So here are the 3D convex hulls. Here I show 2D convex hulls, starting from calcium, sulfur, and H2. And what I note is that there are a number of species that are found on these convex hulls to be thermodynamically stable. CaSH3 is metastable. At high pressures, it is stable. And here I show the convex hull, including the 0-point energy. It's really important in a lot of these hydrogen-rich structures to consider the 0-point energy, because they have so much hydrogen within them that this can actually change the thermodynamic stability, or change which structures are thermodynamically stable. Now, most of these phases, unfortunately, were not interesting for superconductivity. They were not metallic. The only one that was interesting was the CaSH3 phase that I mentioned right here. And what was really interesting about it is that it was comprised of these types of honeycomb lattices of sulfur atoms bonded to hydrogen. So in a way, this is a two-dimensional version of the SH3 structures that has previously been found to be superconducting. So it's a two-dimensional version having these types of honeycomb necks separated by CaH2 layers. And what is really unique is that the density of states at the Fermi level lies close to a Van Hove singularity. Now, within BCS theory, one of the things that can give rise to a high superconducting critical temperature is if you have a high density of states at the Fermi level. So we like the fact that we are sitting close to this Van Hove singularity, because we think that this species could potentially have a high TC. We then estimated the superconducting properties of the CaSH3 phase. TC, the highest TC was about 100 Kelvin at 128 gigapascals, which is not room temperature. It is still quite high, not room temperature, of course. But what is exciting about our work is that it proposes a new family of superconducting species that could be built by, for example, replacing the alkali metal by other alkalis such as magnesium, calcium, strontium, and barium, and also the sulfur by other species such as selenium and tellurium. And we have done preliminary calculations showing that indeed these types of phases could be dynamically stable under pressure. Now I would like to talk about other types of superconducting species, in this case ones that could be quenched to 1 atmosphere, because this hydrogenic cages that I have just shown you will most likely fall apart after the pressure is released, because the hydrogen-hydrogen bond is just not going to be that strong in these three-dimensional carbon clathrate-like lattices. So there are no pure carbon clathrate lattices that are known. However, it was proposed based upon theory in this paper right here, that if you have, if you dope a carbon lattice with boron, and then add small alkali metals to it, you could potentially stabilize these carbon-like lattices under pressures. And then most recently, the group of Timothy Strobel theoretically calculated and experimentally was able to synthesize this strontium boron carbate clathrate under pressure and then quench it to 1 atmosphere. So this made us think of, what about borosilicides? Are there any borosilicides that could have these types of clathrate cage structure, which is very different for the borosilicides that have been made in the past? For example, this clathrate 1 structure prior to our work was the only borosilicide that was known. So we did theoretical calculations on various borosilicide cages, doping with different types of alkali metal atoms. And we took a look at their stability as a function of pressure, both thermodynamic and dynamic stability. And what we found is that the rubidium and cesium borosilicides are dynamically stable at 0 and 10 pascals. And the enthalpy of formation for the formation of the rubidium and potassium silicides are going to be negative under pressure. So therefore, and then we take a look at a chemical pressure analysis to see how the size of the different types of alkali metal atoms influences their stability. We then calculated the electronic structure and bonding of the rubidium borosilicide at 1 atmosphere, found that it was dynamically stable, it was metallic as a whole doped conductor, and the superconducting critical temperature that we estimated was on the order of 14 Kelvin for this species. So now I'll turn to superhard materials, which have a variety of different types of uses in coatings, armors, drilling bits, and here are the superhard materials that are the hardest ones that are known: diamond cubic boron nitride and boron carbide. So there are a couple of crystal structure prediction methods that are well known for the discovery of new superhard materials. For example, Uspex and Calypso. And what they do is that they estimate the hardness of the material using micro-hardness models that basically depend upon the geometry of the crystals, and also on a number of different models which take into account, for example, the bond strength, the ionicity of the systems, and the number of bonds. Now, all of these types of quantities are estimated using some sort of formula. They're not calculated from first principles. And because of that, some of these parameters are quite difficult to estimate, even though the micro-hardness models are fast. There are also macroscopic hardness models available, where they employ either the shear modulus or the bulk modulus to estimate hardness. However, the problem with this is that determining these moduli from first principles, you might need up to 24 independent DFT type calculations, and so getting these estimates can be very computationally intensive. Micro-hardness models have been shown to fail for systems where you do have non-bonded interactions, such as in graphite. They predict unreasonably high hardnesses. But the bonding models within Calypso and Uspex use chemical graph theory to correct for this. However, there are still cases where the micro-hardness models fail. For example, we have this T-carbon allotrope, which is a hypothetical allotrope. It is very porous. And even though each carbon atom is tetrahedrally coordinated, you would not expect them to be very hard. So the Calypso and Uspex still give a reasonably high hardness, whereas the macroscopic hardness models give a much lower hardness prediction. So recently, there have been a number of machine learning algorithms that have been proposed, and they have been built off of these large databases. For example, AFLOW is a large database which has the computative properties of over 3 million entries. And a machine learning model for the bulk moduli and other properties was made by training to the data within AFLOW. So we teamed up with the AFLOW group to try to use this to make a new machine learning algorithm for combined with XtalOpt to predict new superhard materials. So the way that this works is we use XtalOpt to create new structures, optimize them to the nearest local minimum. We send out the structural coordinates to AFLOW. AFLOW then determines the bulk and shear moduli using the machine learning model, and XtalOpt will then use these bulk and shear moduli to determine hardness and use that in accordance with enthalpy to determine which structures are the most stable for bleeding within the evolutionary crystal structure search. So first we wanted to determine which macroscopic hardness model is the best to use. All of the ones that we looked at had a relatively good agreement between first principles, machine learning, and also with experiment. However, the Tetra model was the most robust when looking at hypothetical structures that were created, for example, during the structure search. So the fitness function that we employed in the new algorithm combined both the energy of the structures and also the Vickers hardness that was estimated by using the Tetra model. And we employed this new method towards the carbon system, where we took a look at predicting superhard phases of carbon with 8, 12, 16, and 20 formula units. Here I show the Vickers hardness of the structures that were created versus the energy. In this quadrant, you have stable phases that have low hardness. These would be graphite-like or layered phases. And in this yellow quadrant, we show stable phases that have a high hardness. So that would be diamond-like phases, for example. And we analyzed the phases in the yellow quadrant, found that 36 of them matched previously predicted or synthesized records, and 43 of them were unknown phases that were dynamically stable. Here I show just a couple of the phases that we found that were novel. And we classified them according to little bits. The blue bits are diamond, related to diamond topologically, and the yellow and green bits are topologically related to Lonsdaleite, which is a form of hexagonal diamond. So most of these very hard phases were composed of little bits of diamond or Lonsdaleite. However, we note that this system here was not. It had a very low symmetry and it was disordered and asymmetric, and it has been proposed that also low symmetry could give rise to very hard materials. So could some of these be synthesized under pressure? Here I show a form of N-carbon, which was synthesized under pressure using the cold compression of graphite. And here I show the enthalpies of the calculated superhard phases versus pressure, and I compare them to diamond and to graphite. Note that by about 60 GPa, all of them are going to be more stable than compressed graphite, suggesting that many of these phases could potentially be synthesized given the correct precursor materials and synthesis protocol. So hopefully I have shown you how crystal structure prediction can be used to synthesize, to predict new hydrogen-rich materials that could be superconducting, and also how it can be used to predict new superhard materials. And here are some of the people that have been involved in the work, a number of graduate students and postdoctoral associates. And I would like to thank the Department of Energy, the NSF, CDAC, and the Office of Naval Research for funding this research, as well as my collaborators on high pressure and on superhard materials. And I would like to thank you for your attention.
Thank you very much, Dr. Zurek. We have a couple questions from the live audience. First, in structure prediction, are you also able to predict types of lattice defects which may dominate the system in order to visualize how those defects may affect superconductivity within the system?
Right, so when we do the crystal structure prediction, we try to predict the most stable structures and also important metastable structures for a given stoichiometry. And then we also limit the formula unit cells that we consider within the structure prediction searches. So we focus on those types of systems. Now, there are other methods that might, for example, consider defects specifically. I think that one can create such a crystal structure prediction algorithm. It's just that we would have to probably vary the evolutionary operators, change them somewhat, and also potentially change some of the fitness criteria. So one could do that. We do not, but I think you could build a crystal structure prediction algorithm towards that end.
Thank you. Another question is the iterative, I'm not sure, let me try to say this, XtalOpt and machine learning predictive process seems very powerful. There's a question about how quickly this process can be performed. In other words, how rapidly can one make predictions about a new material using this process?
Yes, so the machine learning estimates of the hardness are, take a second. The slowdown there would be that we have to connect to AFlow to get the results. So that is a potential bottleneck. The biggest bottleneck, however, is the DFT calculations. Just that we have to optimize so many structures to the nearest local minimum. However, I think that there's going to be real advances in this field as people start building machine learning interatomic potentials that could be used within crystal structure prediction and that are accurate for the regions of potential energy landscape being explored. So I think that this is going to speed up a lot, and also that in the future, what one could do is start with a machine learned interatomic potential, and then do DFT calculations during the course of the crystal structure prediction search that are used to refine the potential. And in that case, I think that we'll be able to have really powerful techniques that can be used for much larger unit cells than we have been so far.
Thank you. I think we have time for one last quick question. This is on a related note regarding those predictions. Question is, it was shown that the teeter model is most accurate across the board. Would it be advisable, or are there certain models that perform better in different regimes if you were focused particularly at a given pressure or under a given condition?
Right. Okay, so I'll tell you the main reason why we chose the teeter model. Okay. So if you look here at the correlation coefficients, so here I show experiment versus theory of the AEL, so that's the first principles calculations, and the ML, that's the machine learning. Generally speaking, you can't really decide from these correlation coefficients and so on, the root mean square deviations, which model is better. However, what we found, if you look here, the B, in some cases, this is the original AFlow machine learning model. In some cases, B is very low. And we also found that the machine learned B, in some cases during the crystal structure prediction search, was way too low. Now, in these other models, you see that they use the K, which is the shear modulus divided by the bulk modulus. So if your bulk modulus is much too low, then your K is going to be much too high, and your Vickers hardness just explodes. And so in some cases, we just got unreasonably high Vickers hardnesses for these crystal structures that were, hypothetical, generated in the crystal structure prediction search. They might not ever exist. And because of that, they were found to have a very high Vickers hardness, like 200, 300 gigapascals. And they were then found to be predominant in the breeding pool in the search. So that is the main reason why we chose the teeter model. The other reason is if you look at the dimension of the teeter model, it's going to have the dimension of GPA, whereas here you have strange dimensions coming out of it. And also this coefficient in the teeter model was actually developed theoretically based upon the shape of the Vickers indenter, whereas the Chen and the Tian models were actually these numbers here were developed by fitting to experiment. So those are the three reasons why we chose it. The first one being the most important. However, I have not explored regions where I have just not done it, explored regions where the Chen and Tian model might be more appropriate for predicting the hardness of known materials.
All right, well, thank you very much. Thank you also for presenting and for participating in our CMCC mechanochemistry discussions. We very much appreciate your great presentation. And audience, thank you for participating.
And thank you very much, and best of luck to the success of the center.
Thank you.